Yeah. The objective of this design project is to design a cantilever beam capable of withholding 1,000 Newton force at a maximum of 200 grams mass. In addition, it should strive to be the greatest length out at a maximum of 12 inches and must be manufacturable for testing.
Our research design was based on the equations for stress of a beam. So this top beam was Emmanuel's initial design, and we ended up not using it because it wasn't manufacturable. The second design was Alex's initial design, which also was not manufacturable. And then this third design was mine. And this is the one we ended up using. This screenshot is a prototype. And so we based this design off of the equations for stress of a cantilever beam. And we saw that in order to make the beam the most resistant to stress, we needed to maximize the Y value, which is the height of the beam, and minimize the second moment of inertia. And so that gave us a choice between three different types of cross sections. There was the circular type, the square type, and the I-beam type. And we ruled out the circular type because you can't really control the vertical distance because then it would be more of an oval and you wouldn't be able to stick it in the rig. And the second type is the squared type, and we didn't go with that because compared to the I-beam, it had slightly higher second moment of inertia, and also it has more mass for the same volume. So the I-beam was our best choice. And also, as you can see, we made it kind of a double I-beam so that it sticks into two holes in the rig, and that maximizes the Y value. And that was our thinking for our beam design.
All right, so for our final design, it implements the double I-beam structure, and it's slightly thinner and shorter than the original design. There's also a lip at the bottom, so it could reduce the stress that accumulates at the bottom of the beam. Under the 1,000 load, under the 1,000 Newton load, the maximum stress that it allows is 44,221 psi, and which is lower than the 45,000 psi limit. And it's composed of low carbon steel. It's 12 inches and 198 grams.
The manufacturability of our beam is solid, as it is several rectangular cuts in the blank cast. And our design minimizes the manufacturing costs by limiting the pallet rotations and tool changes needed. The only pallet rotations needed will be to switch from one side to the other and then to the top for the divot for the ball bearing. In addition, there will only be one tool change needed in order to change the radius of cut for the ball bearing. Our design does use steel, which creates a greater cost of cutting to aluminum. However, we thought this was necessary as aluminum yields lower strength than steel.
For risk mitigation, we compared the ultimate tensile stress with the tested stress, and the tested stress is the maximum stress that the part experienced during our testing. And so this is our margin of safety. Take note that it's not a factor of safety, it's a margin of safety, which is the tested stress over the ultimate tensile stress. And so our value was 0.98, which is pretty close to 1. which means we still have a little bit of tweaking to do, but it's not too bad. And we also tested the part with a point load and a ramped load because we figured that in real life, you can't have a perfect point load. You have to kind of approximate for just real life situations. And so we thought a ramp load might be more appropriate for making it more realistic. And so this margin of safety is actually for a ramp load and not a point load. So it's a little bit higher than it would be normally. And again, this is margin of safety. So higher, closer to 1 means less safe, and further from 1 means more safe. Further from 1, below 1. And yeah.
All right. So we pushed our prototype beyond the design limits, making it more resistant to the 1,000 Newton load. Our design is made out of steel, which is sturdier than aluminum, and it's a unique structure. So it makes manufacturing, it keeps the manufacturing at a low cost. Thank you for listening to our presentation, and hope you invest in us.